Okay, let's get started. So far we learned about the baseband modulations, QPSK, QPSK, and how to analyze the error rate and how to simulate all those things. And what we're going to learn from now on is baseband data transmission, which means that we're going to look at the whole system in the big picture. We are not going to look at only the modulation or demodulation. What we're going to look at is we're going to look at the whole picture of the communication systems with the transmitter and receiver. So let's look at here. You see that in the picture we have a transmitter from here to here. So far we have transmitter from here to here. This is a transmitter. We also have a receiver here. This whole thing is a receiver. Between transmitter and receiver, we have a channel. So this channel, maybe it's just noise channel, or it can be like fading, or there are many different channels. And this channel may be a wireless channel, maybe cable, maybe underwater, it doesn't matter. But we have a channel between transmitter and receiver, right? So when you look at this, transmitter has many different parts. Source means original information. We have some original information to transmit. So that information now goes into line encoder and becomes encoded. So now we again get some, actually there is a modulation somewhere here, but you know this picture ignores the modulation. So we have some symbol here after the modulation. So modulation is not an important part in this picture. But after you create the symbol, before you transmit through antenna, you have a transmit filter. Okay, so this part, this block, particular block is called transmit filter. And then you transmit to the channel. Now we have a channel block. This is channel. And after the channel, now we receive it through the antenna. Right after the signal, now we have receive filter. Receive filter is part of the receiver. So this is the first block at the receiver. So this whole thing is done sequentially. You have original information to transmit. Now put the original information to the line encoder or some kind of modulation. After that, you go through the transmit filter and then transmit. Transmitted signal now go into the channel. After the channel, you receive it, right? And after you receive through the antenna, it goes to the RX filter and then go on to the decision-making device or some destination. And originally, you're going to recover the original information back. Okay, so those whole thing is sequential. From left to right, everything is sequentially. Right? So here's a couple of questions. When you look at this block diagram, so far we never talk about these filters. So what is the purpose of this transmit filter? Why do you need this transmit filter? Why do you need that? First reason you need the transmit filter is to make your spectrum, make your spectrum shape. So in order to shape your spectrum. Think about this example, right? Let's say your cell phone is using 1.8 gigahertz, right? As a carrier frequency. Your carrier frequency is 1.8 gigahertz. But the thing is, there are so many different frequencies. But you are supposed to use only 1.8 gigahertz. If you transmit, let's draw here in the frequency. So from here to here, let's say the center is 1.8 gigahertz. And this is, let's say, 10 megahertz bandwidth. So this is the bandwidth given to you, right? So your spectrum should be only inside of your bandwidth. What if you transmit your spectrum like this? What's the problem? If you transmit it this way, right? Right here, right here is not your band. This is your someone else, right? Your someone else. Someone else is using this band. So this is called out. This band is out of band because this is not your band. This is someone else's band, right? This is called out of band. We call this OOB. You should not transmit any power in this out of band because this is not your band, right? Once you do this, what happens? You are interfering. You are interfering as someone else, right? You are interfering other people. So what that basically means is that you need to have some special filter like this. This is filter. You need to have some special filter like this, such that you create your signal, but your signal goes into this filter so that your output has no power in here. That's the requirement. If you have no filter like this, then maybe you are transmitting some out-of-band spectrum like this. So that's not allowed, right? So this is why this filter is sometimes called out-of-band rejection filter. That's another name. You need to have this out-of-band rejection filter because you are supposed to transmit only within your band. You are not supposed to transmit any single power onto the out-of-band because that's used by others, right? And this filter will make sure that your spectrum, your transmit power is only within your band. That's the main reason. And how do you do that? You need to shape your spectrum. If you have this kind of transmit power, then you're going to shape it. You have to cut it here, and you need to shape it. Okay? You need to shape. So that's what you need. Shape in the frequency domain. That's what you need here. So this is the transmit filter. Now once you do this, your spectrum, your transmit power is only within your spectrum, your bandwidth. Now you transmit your signal. That transmitted signal go into the channel, and this channel, again, this channel is any channel. Sometimes it's only noise. Sometimes you have a noise plus some fading. There are many different channels. It's a very bad channel, very, very bad. After this channel, you're going to receive it through the antenna. And first thing to do at the receiver is a receive filter. Why do you need the receive filter? Eliminate the other signal? Yeah, that's one of the, yes, that's one thing. Let's say, as a receiver, right, your cell phone is going to receive all the frequencies because all the frequencies is flying over here, right? 1.8 gigahertz, but there are 100 megahertz, 2 gigahertz, all the frequencies are here. We cannot see it, but all the frequencies are flying over here. And my cell phone is going to take only 1.8 gigahertz. So you need to select your band, right? That's a part of the reason you have filter. So you're going to take only your frequency. And all the other frequency, I don't care, just reject. Okay? Something like that, similar reason. So that's one of the reason. Okay? So this is all out-of-band rejection. This is also going to be band selection. And this is selecting only my band selection filter. So that's one of the reasons. But there's a second reason for these two. First reason is for this one, band selection. Let's say band selection. For this one, band rejection, out-of-band rejection for this one. So this is the first reason for these filters. Second reason for these filters is something else. I'm going to talk about the second reason. Okay, so that's the main thing that I'm going to talk about here on the next slide. Okay, second reason. But before talking about the second reason, what I'm going to show you is that I want to simplify this picture. Look at this whole picture. We have a couple of these blocks at the transmitter. We have one block in the channel. We have many other blocks at the receiver. But from left to right, everything is sequentially, right? From this one, after this, you do this. After this, you do this, right? After this is all sequentially. So that's why what I'm going to do is that I'm going to group these 3 blocks. You see that the red box here, right? I'm going to make these 3 blocks as a group. Group it, right? Group these 3 and make it as one block like this. So it says overall characterized by pulse spectrum. But anyway, whatever it is, this small block here is a combination of these 3. Just put these 3 blocks together and make one block. And then replace it as 1. And the remaining part is same as this part. This one same, right? This part the same. This is a receiver structure. So when you look at the actual system, right? Actual system, here's a transmitter. Here is a receiver in the actual system. So this filter, transfilter, is part of your actual transmitter. This receive filter is a part of your actual receiver, but forget it. Forget the transmit filter, forget the receiver, forget all the actual stuff. Just look at this block diagram and look at everything in a sequential manner, and just replace these 3, put them together, and make it as one. So this is a simple model, right? So when you look at here, input to this block is this one. So this block, this line, and this line is the same. Okay? So put these 3 blocks, group together, and replace it into, make this one. And then what I'm going to do is this transmit filter. This is a filter. So every filter has its filter response, or you can say impulse response of that filter. So of course this filter has its own impulse response. Let's call that as a GT in time domain, or maybe we can say GF in frequency domain. Okay, filter has its own time domain response, also frequency domain response. This channel here, this is also filter. Okay, this is somehow its filter. Why? Because we transmit some signal, that signal goes into the channel block. Whatever you do in the channel, you're going to have some output. So somehow this is a block. There's an input-output relationship. So this one we can also say there is an impulse response of the channel. Also, there's a frequency response of the channel. Same way, filter here, the receive filter, Q, right? Yeah. So this receive filter also has its own time response and frequency response. So we are going to say the transmit filter has a GT, channel impulse response HT, receive filter response as a QT. Okay? Same way, GF, HF, QF. Right? Simply, that's the response. At this point, we don't know what it is. We don't care. We don't care what it is, but there is a impulse response because this is filter and channel. Right? Now, what we are going to do is that we're going to put that all together, 3 blocks all together, and make one block. And this one block, again, has its own response. Time response, PT, and frequency response, let's call this a PF. Okay, so this PT and PF is the time and frequency responses of this block. But what is this block? This block is a combination of these 3 blocks. Now let's take a look at the PT. How can you write the PT? This PT right here. This is a combination of these 3. So how can you write it? Simply, this is a convolution of these 3. These 3, because these 3 blocks are sequential, right? So you can say this is simply a combination or convolution of these 3 blocks, like this. And PF, of course, is simply a multiplication. Very simple like this, right? How do you know? let's say we say this is A. A is the input. And what's going to be the output of this? This output, let's say, is S, right? What is S? ST. This ST, let's write it here. ST, this ST, equals convolution of A and GT, right? Let's call this AT, then AT convoluted with the GT. Because this is output, this is filter impulse response, this is the input. So simply the output is a convolution of these two. Now what's going to be the output from the channel? Let's call this one as XT. This XT, again, same way. This XT equals input to the channel. Input to the channel is ST with a convolution with HT. Same way, right? ST, convolution with HT. But what is ST? ST is this one. So put this one in here. Now we know that this is AT times convoluted with the GT, convolution with HT. You can do the same way for this one, right? There is output YT. What is YT? YT is a convolution of QT and XT. What is XT? XT is this one. So put that all together. Now you can see that PT is actually this. Or maybe you can say YT. Here's YT, right? Here's YT, which is same as this one. So PT has the input AT, the same input, and output YT, this YT. This is the output, right? So what is the output? Output YT in this block, simply YT equals PT convoluted with A input. That's simply the input convoluted with PT, right? But what's PT? Based on this picture, original PT is this one. So put this one in here, then you can see the output, right? That's the relationship. So this whole picture, the up here, and this picture down here is the same thing. Just down here is just a simplification, right? This picture down here is a just simplified picture. Just group them all together and make it as one block, right? That's it. And once you do that, now you can see this kind of convolution relationship. So we'll see that in the next picture. Let's look at it here. So you'll see some of the equations here, but these equations is what I just said, right? I just talked about all these equations. Look at here, what is the PT? PT is convolution of these three. And frequency response PF is the multiplication of these three frequency responses. So that's what I said earlier, right? Yeah, that's what we have here. And this equation here is a kind of intermediate term, right? ST is the AT convoluted with the GT. What was the AT? AT was this one, and this is ST. And the middle here, transfer filter has a response of GT. So that's why GT convolution with A, which is ST. Convolution relationship, right? And XT, what was the XT? This is the output, XT. XT is again the convolution of HT and ST. So HT and ST, but ST is this one. So put this in here, now you can see. And put that all here, then you can get YT like this. And YT is the output. YT is the output here in this block, which is also the output here. Okay? Here's YT. And this is just simplification in this relationship. So this equation is not really difficult to understand. When you look at this one, you know, put that in the convolution relationship, you can easily get these equations. Okay, so let's move on here. Now, what we're going to look at here in this equation is this one. Y is a convolution of A and P, right? YT here is a convolution of A and PT. Okay? We can write it here. This is a convolution equation, right? especially when you have a discrete sample. What is the TB here? TB is a sample, the bit duration, which means that you already have done sampling, right? Based on the sampling frequency, now you have a bits, and each bit has a duration TB. So that's why you've done sampling like here, right? Original PT is analog. Now you get sample every TB point. So that's why that's this one, right? K is from minus infinite to infinite. So every K becomes like a 0, 1, 2, things like that. So when you have a K, you do a sampling at KTB point, so you get a discrete time, discrete sample. And this is the input. So this is simple convolution relationship. Now when you look at this equation, right, what you can see is that based on the definition of convolution, this K goes to minus infinite to infinite. That's the problem. That's the problem, right? Your output YT is a summation of all the P minus KTB. And K becomes minus infinite all the way to the infinite. What does that mean? Did you heard about causal or non-causal system? What does causal mean? Or non-causal mean? So causal system basically means that whatever happens now should affect whatever happens later. You cannot do back to the future thing, right? You cannot do that. So which means that causal system is like the future sample cannot impact the previous samples. That cannot happen, right? Only whatever happens now can affect later. Whatever happens later cannot affect the previous sample. That's impossible. That's the back to the future thing, right? So that's causal. But when you look at here, the K is from minus infinite to infinite. But we get the output at the time at t. This is the output when you have time t. But in order to make the sample, output sample at t, your input or your impulse response or your input sample is from minus infinite to infinite, and you combine all together. So that doesn't make sense, really. That's not causal. This is simply a mathematical notation. This is definitely not causal system, right? But anyway, when you separate this equation, right? Let me write it again. What you want to do is that you want to separate when k equal to 0. Let's put the k equal to 0. Then A0 times, when you put the k equal to 0, this becomes pt plus, because this is summation of all the things, right? Plus k equal to minus infinite to infinite, but k is not 0 because we separate the 0 out. So remove the 0 here. And then akp t minus ktb. We can write it this way, right? So this equation same. What I do is that I just separate the 0 when k equal to 0 out. And these remaining summation has all the other terms but k equal to 0. Okay, k equal to 0 term is out separately. Why do you want to do this? Okay, the reason that I'm writing this way is simply this one. Let's think about a very simple system. We are talking about a block, just one block, which has the impulse response PT, frequency response PF. Our input is AK, and K is from infinite, minus infinite to infinite. And we have output, which is Y, T. Something like this, right? what we want to do is that this output yt is when k equal to 0. Put it another way, this is simple input-output relationship. What we want is, we want to get an input, right after that we want to get an output. So we get some input, then right after that we want to get some output. That's what we want. Which means that we want to have no delay. Let's think about this way. If you get a input, think about this way. Simply, just simple relationship. We have one block. Let's call that as ht, and we have input xt. We have input yt. Then what is the relationship? Yt. What we want is, we want to get yt at the same time that we get input. If we get like this, let's think about this way. No. Let's say we have output y, but yt is same as this. Then what does that mean? If you have this output, what that basically means is that you get an input xt, but 2 times delay. After the 2 delay, you get the output. So there is a delay in this case, right? Because the output time is the t minus 2. So when you get some input at some point, 2 times later, you get output. There's a delay. And we don't want that. We don't want to have a delay. We want to get like this. That's what we want. And not only that, so no delay in this block. That's the first thing. So that's why we have a 0. We separate the 0 out, because this 0 term will have the impulse response as a pt. This t is the same as output yt. So both are t, right? So meaning no delay. So we want to put our term, this term is the output at the same time as the input, right? So no delay between this term. So that's what we want. And not only that, what we want to get is the output like, we want to get output like something like this. What we don't want is, we want to have something like this. We don't want this. What is this one? You can see a lot of this output, right? What that means is, your input xt comes first, and that goes into the memory in the channel. So that basically means that you have 2 terms, right? And one is xt and second is st minus 1. That means this block has a memory. You know what memory means, right? This is not hardware memory. This is not hardware memory, right? This is some block with some memory is just concept. Think about that you go up to the mountain, right? Go to the mountain, right? And you shout at the mountain. Like, then you're gonna hear echo, right? You hear your own voice. Then do you hear just once? There's a multiple thing, right? You say, that means your voice is bouncing back to you like multiple times. Like this, right? What does that mean? That basically means that this environment, when you go up to the mountain, the top of the mountain, that environment has a memory. That's why your voice is stored in the memory, and it's going to be output multiple times. That's a memory concept. So same concept here. Whatever block this is, if you get this kind of output, that means this has a memory. I'm not talking about hardware memory, right? I'm basically talking about the concept. This one has a memory. So because of the memory, if you have no memory, that means you're going to have only one output. Because whatever coming in will be whatever coming out, right? Because there's no memory. Once you have a memory, then the input will be stored inside the memory. and then it goes out at different time. So you're only in that case, you're going to have a multiple like this. Sometimes you have two memories. In this case, you have two memories, right? Two different memory. So when you have a memory, you're going to have a multiple output, multiple samples all mixed together. That's going to be output when you have a memory. This environment or this kind of things happen, very common, when you have a memory in this block. And what we want to do is that we want to have no memory in this block. Or you can call this a memoryless. Memoryless. Because when you have a memory, right? As I said, all these three samples are combined all together. That's the output you have. In that case, it's very difficult to separate because it's all mixed together. How do you separate it? It's very difficult to do it. So that's why what we want to do is that we want to make this block no delay, no memory. That means this block is perfect. So perfect block for us is no memory, no delay. Okay? Then what is a perfect block? Perfect block is something like this. You get some input, right after that you get one output, only one. Whatever you coming in, whatever you're getting in, you're going to get out. Maybe this block is maybe this block is multiplying some gain, like maybe making 2 times bigger or 3 times bigger, or this block maybe turn the phase a little bit. You can do something here, right? It's not simple bypass. You're going to multiply or you're going to do something. But what you want to do is that you want to have no memory. Sometimes delay is okay. Delay doesn't really matter much, but memory really matters. When you have a memory, you're going to have multiple terms all combined together. This is called intersymbol interference. This is called intersymbol interference. ISI. You want to remember this word, ISI. Very important, very common word in communication. And what does it mean? What that means is that between the symbols, inter means between, right? Between symbols, you have interference. One symbol is interfering next symbol. Okay? One symbol is interfering next symbol. That's the intersymbol interference. This is exactly the case of ISI. Why is that? Why is that? Because think about this way. Let's say our t is 3. Just as an example, right? If t equals to 3, that means this is x3, this is x2, this is x1. The output is 3. So what that means is that when the time is 3, x1 is adding. x2 still is there. Why? x1 is a 2 sample before, right? This is a sample 2 times before. x2 is the sample, is the previous sample. Why? Question is why the previous sample or previous sample is still there and impact my output? Why? Because of the memory. And that is ISI because x1 and x2 is impacting y3. Right? It's intersymbol interference. That's intersymbol interference. This is really bad. When you have this ISI, it's really bad. That happens because of the memory. That's why we don't want memory. We want to have no memory. We want to remove the ISI. And in this equation, right? That's why when I have output equal to y equal to 8 convoluted with pt, I just separate it out this way. So the first term here A0 PT. This is the term with no memory. This is the term with no delay. And the remaining term, these are all symbol interference terms. Think about this way. Now, if we can remove this completely, okay? If we can completely remove this, then what's gonna remaining is we're gonna have only YT simply equals to A0 PT. That's what we have, right? If we can get it, if we can make it this way, then this is gonna be like output equals input times impulse response with no delay, with no memory. So this is the eventual relationship we want to have in this block. So we want to make this block to have this input-output relationship. That's what we want. This is our goal. We want to have this one. But what is the reality? Reality is we have so many terms. That's the problem. So now what we need to do? This is what we want, but this is what is actually happening. So what we want to do is we want to kill this. We want to remove this term. That's what we want. Okay? That's eventually what we want. So go to next slide. So this next slide has a bunch of equations, but these all equations is what I just mentioned. Right? So you have, I just explained the whole thing here. So here, when you look at here, this I is the sample index. So this yi is the ith sample, output sample, output. This ith output sample equals this one. This one is simply convolution. But when you look at this convolution, this is a summation of so many different terms, infinite number of terms. But what I want to do is that I want to separate this summation into one plus so many other terms. Why? The first one is the same ith component. This is root square E, AI. So this is also ith component. And all the other remaining term is a summation of all the other things. And those red terms will create ISI, like this. So what we want to do is that we want to remove these red terms, so many summation, we want to remove this. Once we can remove this, then what's going to be our final output? This is going to be our final output. Ith output sample simply equals root square E times AI. AI is the ith input sample. What is AI? AI is ith input sample. So if we can have this relationship, then what that means is whenever you have an input sample, that input sample is simply multiplied with the root square E, and that's going to be your output at the same time. Whatever you input, that's a root square E output immediately. Right? That's the relationship. That means no memory and no delay. Because ith sample comes in, you have ith sample output, so no delay. And no memory because there's no other terms, right? Whatever input, that's going to be your output after you multiply some constant. So no memory. So that's the relationship we have. Okay, so far what we just discussed is that, okay, one more thing here. What we are discussing is the P. P is what we are talking about, right? P. And what was the P? Let's go all the way back. Right now we are talking about this block here. Okay? We are talking about this block. This is a PT, and we have input AI or AK. We have output YT. So far, we are talking about this block. And how do you want to make this block? I want to make this block to be no delay, no memory. I want to make this block no memory, no delay. But what is this block? This block actually is a combination of these three. So what does it mean? That means I want to make these three blocks combined, okay? And then no delay, no memory in this case. What does that mean? That basically means is that if we can make this whole block no memory, no delay, that means whatever you transmit, you're going to receive it with no delay, with no ISI. That's what we want, right? That's the communication. You want to transmit some information with no delay, with no error, no memory. And that's what you're going to receive, right? That's what we want. That's our dream goal. So transmitter, receiver, we want to deliver the information with no memory, no error, right? So that's our goal. So we want to make this block to have no delay, no memory. So that's what we are discussing now. In order to make this, there is a concept called the Nyquist channel. Okay? Nyquist channel is some concept. Okay? And this concept is to provide this whole thing. So now we want to make this block to be, simply speaking, we want to make this block to be Nyquist channel. We want to make this one as Nyquist. Maybe you heard about Nyquist sampling rate, right? Same guy. Nyquist is the name of the guy, right? The same guy. The following his name, we call this Nyquist channel. So this Nyquist channel has some special relationship. And what's the relationship? The relationship is simply, if we can make this block to be Nyquist channel, that means we have no delay, no memory in this block. Simply, that's what we want to do. Now then, since we are talking about Nyquist channel, we want to look at a relationship of this block. Let's say we want to make this block to be no delay, no memory. Then what do you think is going to be the PT? Or what is going to be the PF? If we want to make a no delay, no memory in this block, then what kind of PT or what kind of impulse response do we have? As I said, no delay, no memory means this is a perfect channel, perfect block. What is the perfect response, impulse response? Perfect impulse response is this is a perfect impulse response, right? You have only one impulse at the delay 0. Since we have a 0, that means no delay. If we have, let's take a look at the basic of impulse response. Let's say, let me draw some couple of different impulse response. Let's think about these two impulse response. What is this impulse response? We have only one tab, but this tab is at the time 1. What does that mean? Let's say we have some block. This is input, this is output. We have impulse response HT. Let's say our HT looks like this. Then what happened in this block? If you have this impulse response in this block, what that means is this one has no memory, but there is a delay. There is a delay. How much delay? 1 delay. There is a delay. Now let's say if our impulse response looks like this, right? In that case, what does it mean? That basically means we have now memory. You have 2 tabs. So now we have a memory. Why is that? How do you know? Let's say our HT looks like this. How do you know it's a memory? It has a memory. Very simple, right? Let's say we have, let's say input. And since this is a discrete, let's say, let's call this one as a HN, and our input is also HAN, okay? And YN is the output, let's say. Let's make it as a discrete, everything. If you have this impulse response, and you're gonna get the input AN, then what is gonna be the YN? YN output is, of course, AN convolution with HN, right? So let's say we have AN, any AN, any input. Let's say input, there are so many tabs, but just think about only two. One, this is the input. Let's call this A0. Let's make it as A0, A1. Let's say this is the input. Now the first input, first sample, first input sample is A0. Then what is the output at that time? Let's say Y0. What is the first output? This is impulse response. This is input samples. First input sample, second input sample, things like this. What is going to be the first output? First input sample times what? Let's call this one is H0, this is H1. That's the sample coefficient. This one, right? Yeah. This is your first input, output. What is going to be your second output? Now at the second output, your second input comes in. A1 comes in. So that A1, let's go back. The first input sample comes in. That goes into, that is multiplied with H0. Now when you have a second input comes in, the first input stays in the memory, that moves to the next. And then the second sample goes in and multiply with this. So that's why second input sample is again multiplied with H0 plus the previous sample remains in the memory, that moves to the next. That's how the memory works, right? Look, think about the shift register. You know shift register, right? This is exact same as shift register. When you get an input, then on the next sample, this sample moves to the next memory, right? That's exactly what it is. So the previous sample A0 remains in the memory and moves to the next and multiply with H1. So this is what's happening. And keep going like this, right? So that means your output has ISI, right? Intersymbol interference. So in this case, you have intersymbol interference because of this memory. What about the previous case? In this previous case, what happened is Y0, 0. Y1 equals, let's say this is H0. Y1 equals H0 times A0. Y2, H0 times A1. Something like this, right? So in this case, there's no memory, but you have only delay. But this case, you have a memory, right? So again, these two are not perfect because in this case, there's a delay, so it's not perfect. This case, you have a memory. Again, it's not perfect. So what is a perfect impulse response? This is going to be a perfect impulse response. No delay, no memory. That's a perfect impulse response. Now the question then is, what is the perfect frequency response? Let's say we have one block. What is the perfect impulse, the frequency response? Since this is a perfect impulse response, what is the frequency response? You can take a Fourier transform of this, right? Fourier transform of this will give you flat. So this is a perfect impulse response, time domain response. This is a perfect frequency domain response, right? So once you have these relationship in this block, everything is perfect. So that's what we want. We want to make this block to have this time impulse response and also this frequency response In that case, we make perfect block. But we have some problem here. Big problem. Problem is unfortunately, we cannot make this block to have this frequency response. Why is that? If your block has this frequency response, that means you are using all the frequencies. You cannot use all the frequencies, right? You are going to use only your bandwidth. That's what I said here, right? You're going to use only your bandwidth. You cannot use all the frequency, right? Simply. You're supposed to use only your bandwidth. So it's okay to make a flat, but only within your bandwidth. So your frequency response should be like this, not flat. Flat only within your bandwidth, like this. Okay? That's what you need to do. But now the problem is, if you want to make this frequency response to be rectangle like this, now the time domain response is not going to be this. What's going to be your time domain response? It's going to be sinc function, like this. So that's where you have a problem. Okay. Yeah. So we can. Yeah. I guess we can continue next time. Okay.